Okay, so how do you localize a device that has no network connectivity? Or how do you localize a device that might be in a mixed environment of indoor and outdoor and won't have GNSS? And what as well if that device has really, really severe energy constraints and needs to have an average consumption of only a few microamps? I'm here today to present a new functionality of LR1110 and LR1120, which is round-trip time-of-flight ranging. And I'm joined here today by Luka and by Fabien, excuse me. Luka is CEO of INAS, and he has a great deal of experience looking at the kind of applications that benefit from this kind of technology. And Fabien has experience on the antenna side of things, which are a very, very important consideration and building block in this kind of system. So, that was that slide, apologies. So the presentation is broken down into 3 parts, and then we're going to have a kind of a brainstorm and a bit of a discussion between ourselves and take any questions from you guys that you have, because we've got all the experts in one place today. The 3 parts then are, Luka's going to start by talking about why we need this technology, what kind of applications and use cases are really a fit for it. Secondly, I'll present a little bit some of the technical details about how it works, what the benefits are of this technology. And then finally, Fabien's going to present a little bit about the antennas that are a useful building block, as I say, for these ranging systems. So, Luka, over to you.
Thank you very much. So, jumping in straight on why do we need ranging and how to do ultra-low power positioning. So, presently, the most low-power positioning systems are very simple. Usually, they're VHF trackers, so pinger, which just pings at a specific frequency, and then you get a Yagi antenna and point it at things until you find the direction where that object is, and then you move and track until you come to the actual position. Now, that's not very effective, very secure, or very efficient. And if we want to position devices currently, there's a few technologies we have available. So if we look at a bunch of things, for example, we have Wi-Fi, which is an excellent way of positioning in which building roughly you are, or even closer within buildings if you have a well-mapped number of Wi-Fi routers and antennas placed around the building. However, the range and accuracy are somewhat limited. There's plenty of things for Bluetooth, which you might have seen during COVID, proximity detection, positioning, and all of that, where with the right set of gateways, time of arrival calculations, and so forth, you can determine the position reasonably precisely. However, your total range is super limited. For a much better positioning system, you would use something like ultra-wideband or similar. And for example, this is used in various keychain tags and things like that, which you use to find your wallet and objects. However, all of these technologies, including with RFID, which can be very precise but very short range, have a limitation that don't really work in large spaces. So as soon as you want to take it outside a large building, do it outside or anything like that, they quickly become unavailable and impractical for this. So we'll look at a few examples. Firstly, we start with our dear rhinos. And they're a good example where a lot of the animal tracking today is done still with VHF technology. We also have trackers which have GPS position and tell us where a certain animal or an object is. Now, if you want to do really low-power GPS positioning, you want the GPS receiver to be on for the minimal amount of time, which means you often say, OK, it's fine if I know with 25-meter or 50-meter accuracy where an object is. So you don't want to localize more precisely. And if things are moving, it gets a bit more complicated. Sometimes you want to even detect proximity of, say, an animal to a watering hole or something like that. And the ranging essentially gives us the capability to measure the distance between 2 trackers or a tracker and some other object. And that tells us how close we are to something. And if we move about, we get closer and closer. There's another much more, let's say, painful application here, which is theft recovery. So when your car or bike or motor gets stolen, it is assumed it has a GPS tracker inside. So quite often, you will find these things hidden in basements, in a van or in a shipping container. And what happens in that case? Well, your mobile, LoRaWAN, or some other connectivity will likely still work. So you will know at which base station it's connected, at which gateway, so you will know roughly the location where it is. You can come to the area, and they're like, where it is, I don't have a GPS position. So today, there's some products on the market which use VHF. You get your Yagi antenna out, and again, you're like a hunter following an animal or a stolen car. However, with ranging, you can see, okay, it's here, 500 meters, you drive around a bit, oh, you see I'm 300 meters to it, and so forth, you can converge to the location. Now, that gives you particularly the option when you get really close to the object that you can show there's probable cause something is in the container, in the basement, in the garage, and so forth. And then it's easier to talk with authorities that, hey, you actually need to search this. So ranging is a good way to come close to objects with the same radio, with the same piece of hardware that you already use for all the other communication methods. So Tim can talk us a bit more about what LR enables and how all of this works.
Sure. So you can see here then the products that contain this ranging at sub-gigahertz, which is the sort of newly introduced ranging functionality, are LR1110 and LR1120. And so that comes already with the GNSS functionality and the Wi-Fi scan functionality that also augment the localization capabilities of this technology. Here you can see the full set of technologies that are available in our LoRa products. And here we're focusing, of course, on this round-trip time of flight functionality. So what is ranging exactly? So here I have a pair of LR1110s, and my master broadcasts a ranging request. And that's received by a ranging slave that synchronizes with that incoming ranging request and sends back this synchronized LoRa ranging response. During that whole time, the master has had a clock that's been running, and it allows us to measure the time that's elapsed between the master sending the response and receiving the request. And so because everything's happening at the speed of light, that time of flight is equivalent to a distance. And that allows us then to basically measure the range between the master and the slave devices. So there are a couple of ways that we can use this technology. The first, in the case of finding the vehicle, is kind of a point-to-point link. So what we do is we have a device, and we have the ranging master in our hand, and we can follow in the direction of descending distance and end up locating the slave device that we're seeking. Alternatively, if we can deploy some infrastructure, then there's a possibility of deploying the masters as anchors in a setup, and then sequentially performing ranging operations that allow us to then draw circles of range around each of our anchors that are in known locations. And at the intersection of those points, then that's where we'll find our slave. So obviously, we're at the Things Conference. We've got to bring it back to LoRaWAN as well a little bit. And so here you can see, in the context of a LoRaWAN network, how we might deploy some ranging infrastructure or ranging solution. And the way that we see it work pretty well is if, in the case of infrastructure or point-to-point, those devices are all basically LoRa endpoints. And so the master, or the anchor devices here, will be relaying information about distance. The slave might be relaying its own telemetry information back to the LoRa network. And that gives us the advantage then of basically allowing a seamless integration with existing LoRa infrastructure. It allows us to deploy anchors as low-power, battery-powered end devices. And there are also benefits in terms of duty cycle and things like that, especially in Europe, where we don't spend our LoRa gateways transmit time performing ranging operations. But there are, of course, challenges. We've got this great technology, but the greatest challenge that we always face with round-trip time of flight ranging is multipath. So you can see a couple of examples here. On the top left, we have kind of a plan view of our master and our slave. And you can see that the distance we're actually going to measure isn't the kind of the straight line distance between our master and our slave. It's going to be a kind of reflected radio distance. And so where we're in a built-up environment, that can end up being a sort of a range overestimation. For point-to-point, it works because it sort of leads you through the doors and down the corridors of decreasing distance to find your device. But for localization, that can be an issue. The other issue as well is that there's always multipath. Even when we're line of sight, there's still like a ground bounce reflected path in addition to the direct wave. That means you do end up with multipath effects, even line of sight, that can affect the accuracy. So the answer to that is to use circularly polarized antennas. And luckily, we have Fabien with us here today to explain a bit about circular polarization and how it helps us with ranging and his work on the antennas for that.
Thanks, Tim. So I'm going to present the antenna we have been using for the experiment. So Tim will later on present a comparison between linear antenna and circularly polarized antenna to show the benefit. So I'm going to show you how this small antenna is working. So this is the one that you have been using. So it's based on the very classical antenna geometry, which is named the cloverleaf. So if you look at the antenna, you will see that you have wires in the horizontal position and also wires in the vertical position. And they are arranged in a way where they are going to be fed in orthogonal, with an orthogonal phase. And then it will create this circular polarization. So you have on the right an animation of the antenna, of the current on the antenna. And if you look at simulation, you can see here a simulation of the electric field versus time in a plane. So you can see that basically this antenna is mainly radiating toward horizon, so you have no more radiation towards zenith or down position. And here it's not easy to see, but the vector electric field are rotating. So to see it in a easiest way, I just plot on a line, and you see the electric field that are rotating. So this is exactly what we expect in a circular polarization. So there is some measurement of this antenna. So the antenna is reaching a 0 dB IC gain, and it gets an efficiency of minus 2 dB, which is equivalent to 65–70% of efficiency, which is quite good for a very small antenna like that. And you see the dimension of the antenna, it's about 50 millimeter and 30 millimeter of height. If we look at the pattern, as I mentioned, so this is on the left you have the 3D radiation pattern, so it's really like a dipole, but it's a dipole with a circular polarization, meaning that you are mainly radiating toward horizon. And here on the right, you have a comparison between the left and right hand circular polarization. So this one is right hand, and you can see that there is a huge difference in terms of pattern between the right and the left, which means that we have a good circular polarization. So of course you can use this type of antenna to get circular polarization, but think also that we have been developed a lot of circular polarized antenna, not for terrestrial application, but for satellite application. And for example, you have here the Lacuna terminal. So the Lacuna terminal is using the circular polarization to communicate with the satellite, but it can also communicate with terrestrial device. And if you are interested, we have a demo running on the Lacuna booth, where we make the connection between this small device and the Lacuna terminal. And then the application for that is to be able to have terrestrial communication and then sending the data for the ranging, the results of the ranging directly to the Lacuna satellite. And then, for example, for cattle monitoring, you can see where your animals are. Okay, so I think, Tim, you can show the results.
Yeah. So when we have as you saw in Fabien's slides, when we have a right-hand circularly polarized antenna, it won't receive the opposite polarization, the left-hand circularly polarized signal. And the beauty of that is any reflection of a circularly polarized wave will actually be reversed in polarity. What that means in concrete terms, in terms of ranging then, is you can see here, on the left-hand side, we have the results with a linearly polarized antenna. So this is just a regular antenna, the kind of thing that we get on our development kits. You can see in the blue curve then is a measure of, on the x-axis we have ground truth, the real distance, and the y-axis is the measured distance. And so you can see then there's also the red curve, which is actually kind of the path loss, basically. So you can see there's little peaks in the path loss, or pretty pronounced peaks in the path loss at 10 meters and at 40 meters. And what's happening there is we're seeing the multipath result in sort of destructive interference. And the linearly polarized antenna has no way of discriminating that, basically. And so it results in these range underestimations. So you see these, everywhere there are those peaks in the path loss, we see these dips in the measured range. Underneath is the measured precision as a standard deviation. You can see in those peaked areas we're at about precision, so like a spread of ranging results of about 5 meters. Outside of those areas, we're down to the 2-3 meter range. With the circularly polarized antennas, you can see that the blue curve is much tighter, and we don't suffer half as badly in those range underestimations in the curve. And you can see as well underneath the spread of the ranging results is at or below about a meter in terms of standard deviation at least. So it's a big improvement moving from linear to circular polarization where we can with this technology. Okay, so we've got this very low energy way of performing a localization operation. Here you can see some example current consumption figures. For the master, it spends about 2/3 of its time in transmit, 1/3 in receive. The opposite is true for the slave. We've got the benefits of LoRa in terms of performing very long-range point-to-point localization operations. The benefit of using existing LoRa gateways for long-range connections to anchors, to end devices, to ranging slaves. And it also allows us then to deploy ranging infrastructure which will mean that many anchors will potentially see a ranging slave and give us a more precise indication of location. And where this technology really shines is then in places where there is no coverage or where we're in a mix of indoor and outdoor but still need localization. So if you think of something like a large warehouse, aerospace hangars, those kinds of environments where perhaps you've got assets indoors and outdoors, they're the kind of places where this localization technology really shines. And also, we're completely independent of anything outside. We don't rely on GNSS signals, and it's completely self-contained, but still gives good accuracy. So how do you try ranging with LR1110? Well, the answer is if you have LR1110 or LR1120, then you already have it. And so here we've got links to an application note, driver code, and these QR codes up here. And if you don't already have LR1110, then there's also the link to where to find the evaluation kits. So that's it in terms of slides. While you guys are thinking of questions to ask us, I was wondering, Luka, you mentioned a couple of use cases there. I just wondered if you had any more more industrial examples of use cases for ranging.
Sure. So I've mentioned two, most, let's say, common ones we see talking about. There's an interesting one you will see tomorrow about search and rescue. So there will be a cool demo and session separately on that. So that's for tomorrow. The other ones that we can consider are anything like logistics tracking, a lot of pallets and warehouse type of situations. Where you essentially want to track the position of the item itself in its normal course of life. Normal LoRa sensor positioned here on a truck goes somewhere else. You always know where it is. However, you have, say, the warehouses and places like that where you want to very specifically locate it and know where it is. Where this comes in very handy because otherwise you would need some other technology for that positioning. Particularly also for finding things. As mentioned, theft is one, but anywhere where you may want to locate the item, this is a good go to locator mode type of thing and go find the device. As it brings you closer, gives you the direction, and you can easily walk around a bit and get a heat map of the position. And again, in industrial cases, that might be finding barrels, finding pallets, finding lost shipments, finding lost equipment, tools, anything of that sort, but where finding is just part of the application. Mm-hmm. And tracking is the other, let's say, overarching part. So this we can consider as added value on top of that.
Okay, cool, thanks. Any questions from the audience at all? One here.
You mean the gain of the antenna? It's 0 dBIC. So 0 dBIC, yeah. So think that it's like a dipole. So the antenna has a 2 dB, minus 2 dB efficiency. So a dipole is 2 dB of gain, and then you just subtract 2.
Yep.
So is the rating compatible with the SX1280 rating?
So unfortunately, not at this time. So the ranging at the moment this is purely sub-gigahertz for now. So yeah, that's right. So we have a previous generation of product, SX1280 at 2.4 gigahertz, that also has this round-trip time of flight functionality. But this is a new and separate sub-gigahertz ranging functionality. Well, yeah, another question? Yeah, so that's a good question. So the way that it normally works is there's some kind of protocol that sits over the top, because you don't want to be doing ranging the whole time, and you only want to localize a specific device. So exactly. So there'll be a protocol where, I don't know, the slave will periodically wake from sleep mode for a very short window of time and check to see if there's anything in the air. And then you'll find a device, you'll hit the button, and that will send something like a long preamble. And so you have a preamble sampling MAC where the slave device will wake up. Okay, I can see something in the air. Is it for me? It listens to that packet, and then it goes, okay, I've just been asked to do some ranging. I send an acknowledgement back, put myself in ranging mode, and then we start the exchange. So that you get the benefits of authentication and of low consumption as well at the same time.
And maybe to add on top, you can quite well synchronize the devices between them with the method Tim just described, that they roughly expect when the window for ranging is. So let's say devices every full minute go into ranging mode. For example, you can quite well align them that way, and they will feed off the master to see when it's sending out the requests. Mm-hmm. They find one request and know the next one will be in roughly the same period, which is 60 seconds or so, and you can be reasonably low power with just a simple mechanism like that. Although from the network side, you can also control it if you'd like.
Yeah. So I didn't really labor the low power, actually. And just to give you an idea on the slave side, so for the figures that are quoted here, I think it was if you do one ranging every second with the ranging slave, that translates into about 5.5 milliamps of consumption. If you did it once a minute, then that falls to about 90-ish microamps of consumption over that time. So it really is a very low consumption way of doing pretty precise tracking and localization. Yeah, another question, Maroon.
So which spreading factors does it work with?
So it should work over all spreading factors. SF and 11 and 12 we haven't tested so much, but yeah, it's certainly over that range up to 10. It's good. 11 and 12 is still a new technology. We haven't played with it that much, so. But yeah, there will be full guidance going into the data sheet imminently.
Tim, maybe you should comment also on the bandwidth, because it's quite unusual to use a 500 megahertz bandwidth.
Right, so there's, in terms of the optimizing the LoRa modem, we're all pretty familiar. If you sort of imagine you've got data rate and you have your SF, and so you go from like say a high data rate all the way down to a low data rate at SF12 and a low bandwidth. That gives you the best LoRa range. Or you can go to the other extreme where you have a high bandwidth and a low SF, and that gives you the highest throughput but the shortest range. And actually what's best for ranging is high SF and high bandwidth, because that gives you the most integration time and the most temporal information in the channel if you increase your spreading factor and you increase your bandwidth. So it's kind of a third point to kind of optimize for when you're thinking about communicating with LoRa. But that's another benefit of having anchors and things separate from the gateway, because you can do your ranging operations at settings optimized for ranging, and then you're doing your comms at settings that are optimized for the comms. One more question. We've got 20 seconds, apparently.
No, time is up. You
Yeah,
still
all right.
increasing.
Time is up. It's going over. All right. Well, apparently that's it. So, yeah, thank you very much for your time. I hope
Thanks
it
a
was
lot.
interesting.
Thank you.
If you have any more questions, then, yeah, come and find us.